Bismillah ar-Rahman ar-Rahim. Today I'm going to talk about a very important topic, and that is how to calculate sample size for disease prevalence studies. I just selected this topic because there's a problem with samples calculation whenever students are doing studies or planning studies. They don't take care of the sample size, and I have seen it on many occasions that many of the students don't even realize the importance of this very important first step when they are designing their studies. So let's get started. Uh, this is the outline of this presentation. If you want to understand it fully and to come up with real sample sizes for your studies, then you must listen to each and everything in this presentation. So first I would be talking about the importance of sample size for your study, whether too big or too small number of samples would do any good for your study or not. Second, I would talk about the impact of population size on your sample size, whether increasing population density or increasing the population has anything to do with the sample size. Then I will talk about sample calculation formula that you can use to calculate your sample load, and then after that I will discuss about the rationale of calculating the expected prevalence proportion, and I will tell you how to calculate that and what is the rationale behind that. Then I will tell you about the rationale of calculating precision D, which is again very important for figuring out the exact number of samples that you need for your study. Then I would talk about the confidence level. All these things are part of the formula that you would be using for estimation of your sample size. Then after that, I would just show you a tutorial in which I would show, that how to calculate the sample size using this particular formula. And then I will talk about the sample size calculation using different softwares, because there are a lot of online tools for this particular purpose. So to start with the sample size, what is the sample size? This is the minimum sample number you need to uh, estimate the true population portion with the required margin of error and confidence level. you know when you are going to conduct a study, then you plan about the sample size, that how many samples actually you need to conduct that study and to come up with results that are reliable. The confidence level is indicating that kind of reliability of your study, and how much margin of error is there, because you are presenting your results with the confidence level and margin of error. Whenever you see results in different research papers, you would understand that there always they would mention that 90% or 95% or 99% confidence level, and when this much margin of error. Okay, so the sample size is the minimum number of samples you need to estimate the true population proportion, that you want to know that this particular sample size is representing the entire population, because it's not possible by any means to sample entire population for a particular condition or a disease. That's why you take a representative sample from the population. You just take samples of some individuals that you calculate would be sufficient to give you a representation on a population level. Okay, so here are some important tips that you must keep in mind. You should note that if some people choose not to respond, they cannot be included in your sample. And so if non-response is a possibility, your sample size will have to be increased accordingly. You know, I have seen this on many occasions. Students and teachers, they would come to me and they would ask questions about this thing, or when they are presenting their data, they would say that, well, many people, they didn't respond to our questionnaire, they didn't respond to or call for sampling, or they didn't participate. So that does not amount to the your sample size. You must exclude such kind of samples from your data. And another thing is that if you expect that some people would not cooperate for that particular study, then you should altogether go for increasing the number of samples in order to have the real number of samples representing a population proportion. In general, the higher the response rate, the better the estimate is. Non-response will often lead to biases in your estimate. So you must be very careful about it. Then some people say the larger the sample size, the better the study. Is it true? We should determine whether this particular saying is true, that if you just increase the number of sample, okay, it would be good for your study, and it would come up with very good results. Many people have this particular misconception in their mind that by increasing the number of samples, they can just increase to the authenticity of the study, or they would come up with more authentic data about a particular condition. Okay, but this is not true always. It may not be true in certain conditions, because, for instance, in this condition, one of the aims of applying appropriate sample size calculation formula is not to obtain the biggest sample size ever. The job of a researcher is to come up with authentic results, by utilizing minimum number of samples, minimum required number of samples, or optimum number of samples, not, the biggest number of samples, because you can lose on many things in your study if you are just, going to so the aim is to get an optimum or adequate sample size. Unnecessarily large sample size is not cost effective, or it would cost you more. So the job of a researcher is to minimize the cost of studies. Every researcher would tend to do that. So that's why it's not desirable just to go for a bigger sample size. In some circumstances, it is unethical to go for a larger sample size. For instance, in drug trials, a very large sample would lead to a conclusion that the new drug is significantly better than an old drug, in the statistical sense, although the difference may be clinically insignificant. So that would give a wrong message to the clinicians and other people concerned, that the new drug is better, but in reality, it would not be better. So that's why, bigger sample size is not always the answer to, get reliable data. What is the impact of population size and sample size? If your population is large, for instance, very large, but you don't know how large that population is. So in that case, you can conservatively use 100,000, this figure, 100,000. The sample size does not change much for populations larger than 100,000, okay? There is not a great deal of increase in the sample size when the population exceeds this particular limit. So you can just, keep it 100,000, and again, you can get reliable results for whatever the population you are going to figure out the prevalence in. So calculating sample size for your study, it can be accomplished in two steps, and you must remember these two steps. Number first, you calculate for infinite population manually using formula. Okay, and number two is to adjust the sample size to required population. You can adjust it to 100,000 and that would be sufficient for you. So first you use the formula to figure it out for infinite population, and then you do the necessary adjustment. I would just tell you in the tutorial that how can you accomplish this particular task. Okay, here, another method is to simply use online statistical programs. There are programs, statistical programs, where you can just do some adjustments to different parameters, and you can figure out this particular, sample size. This is the formula for sample size calculation. If you are dealing with infinite population, so first you have to describe uh, you have to figure it out using this particular formula, which is n is equal to z square p 1 minus p over d square. N is the sample size that you are going to calculate. And Z is statistic for a level of confidence. There is a table available that I would show you from where you can just take out the Z value in terms of level of confidence. It may be 95% at 95% confidence, or 90%, or 99%. The Z values are variable, so you can just pick it from the table. Similarly, P is the expected prevalence or proportion. In proportion of 1, if 20% P is equal to minus 2. You represent 20% as P is equal to minus 2, and D is the precision. We also call it, the margin of error. So you should define this particular margin of error, or you should define precision, that how precise your data will be. And that is defined by this plus and minus proportions that you go give along with your population size. And this D in a proportion of 1, uh, if 5%, D would be equal to 0.05. If you are just using a precision of 5%, then you can just use this particular value, 0.05, in this particular formula. So you remember the formula, and then we discuss these different terms one by one. What is the confidence level? First, we describe the confidence level. The confidence level is the probability that the margin of error contains the true population. The margin of error, or the precision that you have given in the form of this plus and minus 10%, plus and minus 5%, plus and minus 20%, along with your with the actual value that you have determined, is this confidence level is telling you about that the real proportion or the real prevalence of that particular disease would be in between these plus and minus values, plus and minus 10%. It means that if you take for instance, if you sample the entire population for a particular disease, the data in 95% of instances, if you repeat this experiment with the same sample size that you have chosen, the results would almost be similar. So 95% confidence interval, if the study was repeated in the range calculated each time, you would expect the true value to lie within these ranges on 95% of occasions. This plus 10% or minus 10%, plus 20% or minus 20% that comes along with your sample size. So the real proportion or the real prevalence would lie between these values, plus and minus. Okay. Uh, the higher the confidence level, the more certain you can be that the interval contains the true proportion. If you increase the confidence level, it increases the chances that the true proportion or true prevalence of a particular condition would be in the interval given. The interval is from, for instance, plus 10 plus minus 10 means plus 10, from plus 10 to minus 10. So it is about 20%. So for instance, if the disease prevalence is 30 plus or minus 10%, so it can be 40% or it can be 20%. So the actual prevalence of the disease would be between 20% and 40%. That is, you can increase the level of confidence, and with that, you would have more confidence in telling that about the particular the prevalence of a disease, that where would it lie between these two levels. So this is the desired confidence level. You can just see other tables here, but most of the studies, they are using 90%, 95%, or 99%. And the Z-score for these values is also given in the table, so you just can pick it from there. If you are using 90% confidence interval, for instance, you can, in the formula, put 1.645 instead of Z. Okay. Similarly, if you are using 95% confidence interval, if you want to have more confidence in your data, then this value also increases. Z score would be 1.96. You would put this particular thing in the formula. Similarly, in case of 99% confidence, you can put this Z score 2.576. These are already defined. You can just pick it and put it in the formula, where you are putting other values in the formula to figure out your sample size. Similarly, now we discuss other terms like the sample proportion. We represent it by P. We also call it expected prevalence, so you can also write it as PXEXP, or expected prevalence of a condition or a disease. When you ask about it from researcher or investigators, their common response is that we don't know this P. That is why we want to conduct this particular study, which is not a proper response that an investigator should just come up with. Okay. This expected prevalence of the disease, you cannot conduct a study by just telling that you want to figure out the expected prevalence of a study. For this, you have to why you have to figure it out, that what is the exact P, because it is responsible for variations in your data. The sample size varies depending on this P. If you look at P in the formula, then you can figure out quite easily that it would have some impact on the sample size that you are calculating. This is the proportion that investigator would estimate by the study. Okay. And that's what the investigator usually say. Its value, the value of P, it ranges from 0 to 1, and it has to figure out for correct estimation of the sample size. If you want your sample size to be correct and representative of the population, then you have to figure out this particular P first, and then put that particular value in the formula. It can be determined by in two different ways. Using the results from a previous survey, you can just use the results of previous survey or previous studies that were published on the with respect to that particular disease that you are studying. For instance, if you are going to determine the sample size for hepatitis C virus in a particular region, then you just go and search on the internet, and uh, uh, figure out from the papers that what percentage people, or what prevalence has been recorded earlier by other investigators, and you can just calculate this P or give that value in this equation as mentioned in the paper, or by running a small pilot study. If there is no data, on the conditions that you are going to investigate, then of course you can go for a pilot study, do a small scale study to figure out in a particular town that what will be the prevalence, and then put that particular value in the equation. If you are absolutely unsure, then you can use this P, or expected prevalence, as 50%, which is conservative and gives the largest sample size. If you absolutely don't know, if you cannot conduct any small pilot study due to certain limitations, then you can use 50% is the value, or zero point 0.5 in other terms, is the value of P here. So the population proportion P, preferably P from the studies with similar study design, and study population from the most recent studies would be most preferable. You just go on the internet and find out studies which are recently published and which have similar designs as your study, and have similar study populations. So in that case, you can use that particular value in your formula. If we have ranges of P, for example, from 20 to 30%, a disease has been mentioned in the literature that its prevalence ranges from 20% to 30%, or from 60% to 80%, or 40% to 60%. So which one to select for larger sample size? You would select a sample that would give you a larger sample size. So in case when the range is from 20 to 30%, you select 30%, which will give you larger sample size. Similarly, if the range is from 60 to 80%, you go for 60%, it will give you a larger sample size. Similarly, if it is from 40 to 60%, then you go for 50%, and that 50% can give you or ensure a larger sample size. Similarly, uh, does P equal to zero point 0.5 or 50%, as we mentioned, always ensure larger sample size? As I told you before, that if you absolutely are not sure and if you cannot conduct a pilot study, then you just go for 50%. That this disease probably would be present in, you know, these much people. The expected prevalence is 50%. Or in the formula, it would be 0.5, because as I told you about the value, the p-value is from 0 to 1. So 50% would be 0.5. You can put this value in there. But can it ensure large sample size? Yes, if prevalence of a disease is between 10% and 90%. There are many diseases which are lying in this particular range from 10% to 90%. So in most of the cases, it can be true, or it can work. But no, if the prevalence of a disease is higher than 90% or lower than 10%, which in case of rare diseases happens, some of the diseases would be present in only 1% or less than 1% of the population, which are called rare diseases. So in this case, if the prevalence is more than 90%, disease is highly contagious, highly endemic, or the disease is rare, less than 10%, in those cases, this value P of 50% or 0.5 would not work, or it would not give you, the real sample size. Example, you would understand it from this example very clearly. Suppose you calculate sample size with P equal to 0.05 and D, equal to 0.02. D is usually half of this P, which is 385. For instance, you took this value of P and D as 0.02, and you calculated the sample size for your study. So if you put these two values in the formula, you get the sample number 385. So in case if the real P is 1%, not, 0.05, then, what would happen in that case? If the real P is 1%, in that case, you would get, 1% would be 0.01. You may not get any case are just 3 to 4 disease cases in 385. So your sample load or your calculated sample size is telling you that if the disease prevalence is 1%, for instance, and you have taken it as 5%, then you may not get any case or just 3 to 4 cases in your entire sample load. It means your data would not be correct. It would be misleading in many senses. Similarly, if P is more than 90%, disease is highly prevalent, you may not get any non-cases among 385. The disease that you are going to study, the prevalence of the disease that you are going to figure out, if that disease, if the p-value is more than 90% or 0.9, so in that case, again, you may not get any cases, any non-cases among 385. It means that majority of the cases would be positive in that case, so the study would be wrong. The results would be wrong in that case. These two conditions may not meet the assumptions of normal approximation. What is normal approximation? The two conditions that I mentioned here would not meet this assumption of normal approximation. This approximation is that NP, 1 minus P, must be greater than 5. Small sample size will therefore not work, and after sample size calculation, these assumptions should be tested. You can test it. You have the value of P. Okay, you have N, and you just multiply it with N, or you just figure it out 1 minus P. You can just easily figure out whether the value, the resultant value, is more than 5 or less than 5. Okay, so if it is less than 5, it means your study is faulty and this sample size is not suitable for your study. The second thing, very important thing in the formula is precision D. This precision refers to the actual uncertainty in a quantity, the actual uncertainty in a quantity, because you cannot be certain when you are not able to sample the entire population for a condition, then you cannot be 100% sure. In that case, there would be some kind of uncertainty in your results. For example, prevalence of TB is 20% plus or minus 10%. The absolute uncertainty is 10%. Uncertainty may be absolute or relative, but I'm not going into the details of this. You just remember this value, 20% is prevalence plus or minus 10%. Okay, the absolute uncertainty here is 10%. It means that this prevalence can be 30%, or this prevalence at the same time could be 10%. So the actual value would lie between 10% and 30%. The actual prevalence of the disease that you are going to figure out would be between these two margins, 10% and 30%. Okay, so precision D, it is very important for an investigator to understand this value well. You must understand this value well when you are going to calculate your sample size, because the sample size varies inversely with the square of the precision D2. D2 is below, that in the equation you can say that the square root of it is below the line. It means that something that is up, which is P and Z values, these would be divided by D2, this particular value. That's why it's very important to be precise about your sample size. Precision, we also call it, the margin of error, So you should define the margin of error. It's very important for the study to define the margin of error. And in that case, people can just, decide about the reliability of the data that is being studied. At the end of a study, we need to present the prevalence with its 95% confidence interval. For instance, the prevalence in a sample is 40% and 95% confidence interval is 30% to 50%. Okay, so the prevalence is 40%. Your value is 40%, but at 95% confidence interval, it lies between 30% to 50%. Okay, it means that the study has estimated the population prevalence is between 30% and 50%. Okay? It is between these two margins. And please notice that the precision D for this estimation is 10%. 40% plus or minus 10% equals to 30% to 50%. It means 40 plus 10, 50. 40 minus 10 would be 30. Okay. It shows that the width of the confidence interval is 2 times of the precision. Width of confidence interval is 2D. Uh, you know, in this case, you can see it very clearly that the width of the confidence interval is very important. It's about 20% in this case, from 30% to 50%. So from 30 to 50 are 20 digits, 20%. You know? So it's a long, width of the confidence interval, and when this confidence interval, the width of the confidence interval is larger, like more than 10%, it's 20%, then it's not a good study, and it's not a good estimation of prevalence of a particular condition. It means that you should just go for narrowing this particular window. 20% is too wide of it. If you want it to be 10% or 0.1, then D should be 0.05, So in that case, you can just go for D as 0.05 in your study, and you can calculate D.05 can give you about 20. About 10%, the width of 10%. It would be like uh, you know uh, it would be far lesser. The weight would be far narrower as compared to this particular window that you see here. What is the appropriate D for prevalence studies? This is a very important question, and investigators usually, they describe the study limitations and don't attempt to get high precision. Precision is very important, but most of the investigators, they would not take great care, and they would just, start to describe the study limitations, that we did not have enough resources to conduct the studies, or we had some other kind of limitations, which is not a proper approach. Sample size should be calculated with a reasonable or acceptable precision, and only then certain limitations may be allowed. When you do your best, and you come up with a reasonable or acceptable precision, or D value for D, then you can allow certain limitations, but you should not start altogether with limitations, because that is not a good sign, and it points towards the reliability or unreliability of studies. If the disease prevalence is between 10% to 90%, keep D as 5%, as it would ensure higher sample size. If you keep D as 5%, in the case of diseases that lie between 10% and 90%, we are talking about the prevalence here. So in that case, you can keep D as 5%, and it can give you, a larger or higher sample size. This precision will give a width of 10% to the confidence interval. It means from 30% to 40%, or from 50% to 60%. So it would give a value of 10% here. So if the prevalence is less than 10%, or more than 90%, the prevalence of a condition that you are going to study is less than 10% or more than 90%, D of 0.5 will not work. This particular D, 5% or 0.5, will not work. For rare diseases, for instance, the prevalence of which is 1% or less, at 95% confidence interval, you will get irrelevant lower bound or larger upper bound values, it would be the same situation as we discussed earlier, that if a disease is not very much prevalent, it is rare, and you use 50 this 5% or zero point 0.5 d, in that case you can get irrelevant lower bound negative values, or positive values, larger values, which would not actually be true. That is because of this d value, the wrong d value that you have put in the equation. Therefore, keep d as half of p in cases when p is zero point 0.1 or 10% or zero point 0.9 or 90%. Okay, between 10% and 90%, you can keep d as half of p. You know, we have defined p before, or the population proportion, or prevalence, expected prevalence before. So you can keep the precision value, or d value, is half of that. Okay, when we have this situation, the disease is from 10 to 90% prevalent. For example, if you keep this p-value as 0.04, the expected prevalence is 0.04, then the d value would be 0.02. Or if it is 0.98, you can use d as 0.01. In this case, if P is 0.98, or the disease is more than 90% prevalent, then you should use this particular value of 0.01, not the half that we have used here in this case, where the disease is between 10% and 90%. However, in cases of resource limitations, larger D can be used. When you say that you do not have resources for the study, then you can go for using higher value of do. So here is this short tutorial or example. The question is, calculate sample size to figure out the prevalence of a disease in an infinite population size at 95% confidence interval and 5% precision, or margin of error. Okay, the precision is 5%. So this is the formula: n is equal to z square and to p expected 1 minus p expected over d square. This is the same formula, just a different expression here for the p expected. Okay, so at 95% confidence interval, as we have seen in the table before, and you can check it again in the table, that the Z value for 95% confidence interval is 1.96. So you just put 1.96 instead of Z 1.96 square, it would become, okay? And 5% precision, so that is precision is actually the D value. And in this case, we assume that we absolutely don't know about the population proportion or expected prevalence of the disease. So we have kept it at 50%. As its value is from 0 to 1, so we would just represent 50% as 0.5. Okay, let's just put it in the equation: 0.5. 1 minus p expected again is 0.5 over d square. D square is the precision, or the margin of error, which is 0.05 in the case here. In order to get a larger sample size here, it's between 10% and 90%, so it's safe to use 0.05 here. Okay, so here, when you do these calculations, you get this particular number of your sample size. The sample size for conducting this particular study is 384.16. Okay, so this is the first step that you do. You first describe the sample number, that how many samples you require for this particular study. For the infinite population, this is 384.16. Okay, so keep these values p and d in mind. We have just used 50% or 0.5 p and 0.05 or 5% D, okay, which is safe. Here in this case, as you would go through the previous slides, I have told you that why it should be safe in conditions where the disease is prevalent between 10% to 90%. Okay, so this is the value that these many samples are needed for this particular study or this particular condition, prevalence determination of this particular condition. Now adjust the sample size to a population of 100,000. And I have given you initially in our first slides the rationale behind it, that if you just give this rationale, this number 100,000 it is not very much dependent upon the sample size does not increase very much with increase in the populations above 100,000. That's why you can just calculate it for 100,000, and again your study will be correct and right. So for instance, the adjusted sample size is S. The formula that you would use here is S is equal to S over 1 plus S minus 1 or the population that you are going to adjust this particular sample size or sample number. Also, the adjusted size, you just put these values in here and put your population size here and do the calculations. So you will get this adjusted number. It is 383. So it means for 100,000 people, 383 samples would be sufficient to conduct this particular study or prevalence of the condition with 95% confidence interval and 5% precision or 5% margin of error. Okay, so at 95% confidence interval and 5% D of precision, you can use this sample number. The value that you would get again would be represented with these things. When you would write a paper or reproduce your results, then you would write these figures: 95% confident interval and 5% precision along with your results. So though these results, it means that if you repeat these results in a similar population with a similar precision ratio, 95% of cases you will get, the same results. Where can you use this particular method? It cannot be used anywhere. Like you cannot use it for all different kind of sampling techniques or study designs that you are using. You can use it for simple random designs where you are doing simple random sampling. It's a technique you can just go on the internet and find it about it. Or it's not, for cluster or multi-stage sampling. A cluster or multi-stage sampling is a different technique. It's a different study design. So you cannot use the same formula here. Here for these studies, you can find other formulas. Similarly, use design correction for other designs. If you are using, for instance, cluster or multi-stage sampling, that kind of designs, then you can use corrections. Design corrections in the formula for that. There is, a method available. If you are using software, just change the value because that value is usually 2 for these clusters or multi-stage designs, and it is for simple random designs it would just be 1. Okay, so you can also go for this kind of corrections in the formula as well as in the software there's uses. So there are a number of different softwares that you can use in order to figure out samples easily. There are a lot of them on the internet, and RawSoft is one of them. And just type it in the Google and you would get this particular directed to this particular site where you can just define your margin of error here, what confidence level you need, 90%, 95%, or whatever. What is your population size, 100,000 or more than 100,000? What is the response, distribution? Lead this as 50%. It would be just like the population proportion. Keep it at 50%. Most of the softwares are telling that keep it at 50%. But looking at your study design, the samples that you need, the prevalence of your study, the precision that you need. You can do adjustment to these conditions, as I told you, in different steps, and the software will calculate the sample size automatically for you. Okay. For instance, in this example, this is a 4% margin of error, 95% confident interval, 10 million population, 50% p-value. The sample size that it has calculated is 601. Okay, so these are just a couple of methods which are used for sample calculation. uh, if I have missed on something or mixed up something, then you can just forgive me, especially about these values, zero point 0.5 or zero point 0.05 in the cases of D and P, etc. So don't mix them up. P and D are separate values. Your sample size depends upon the P value as well as upon the D values. And the confidence interval that we are talking about, the z-score in the formula, can be just derived from the table that I have shown you. This particular table, put it in the formula, you know, and figure out the expected prevalence in your about of your disease from the published literature, or do some pilot scale study. Or if you cannot do either of them, then you can just use it as 50%. So thank you very much. I think now the student would understand how to calculate the sample size for their studies. Students in social sciences can also figure out their sample size, for different kind of surveys that they do, like in social sciences or something. But this is very important step, the most important step in your study, and it determines the reliability of your study, and it should be shared with other people or other students, researchers who are interested to do these epidemiological or prevalence studies, and hope that I would share more research tips with you on GTV education. And you can subscribe to my channel and allow these videos to appear in the settings, and then you will get notifications about the research tips that I would share with you from time to time. Thank you very much.